This project will investigate the relationship between biology and computational design thinking as a tool to drive the design of a regenerative architectural solution, focusing on coding and scripting, 3D printing, and material innovation. I'll start by introducing the site. Sydney Olympic Park is located on the Parramatta River catchment with a strong relationship to its surrounding estuary. Its ecosystem has provided the Wangal people with resources for 28,000 years. During European settlement, the site underwent dramatic change and degradations in land and water quality. However, the 80s saw great remediation and renewal, preparing itself for hosting the 2000 Olympics. Today, it's a premier destination for sports, leisure, recreation, living and nature conservation. A 2030 master plan will ensure Sydney Olympic Park becomes an active and vibrant town centre, whilst protecting and enhancing public domain and parklands. It's a node between Sydney's two ever-growing CBDs, whose urban fabrics are quite dense. With a large percentage of its land conserved and protected, Sydney Olympic Park is less dense but faces pressures of mitigating urbanisation, whilst maintaining ecological conservation and biodiversity values. There are four main wicked problems the site is currently facing: more water, more salt, more people, and more heat. All have profound impacts on our health and our supporting ecosystems. But these four problems provide unique opportunities to design regenerative architecture that grows with the site, just as nature has for billions of years. The site is susceptible to dramatic changes in coastline over the next century. Altered rain patterns, sea level rise, lack of tidal exchange, and ocean acidification causes many issues, including algal blooms, that suffocate estuaries, native fish, birds, and mangroves. While these wicked problems seem out of our control, there's a unique opportunity to problem solve here. The site has three main sectors: Armoury Park, Haslam's Park, and Bicentennial Park. The proposed Discovery Centre will be located within Bicentennial Park for its strong connection to vital ecosystems. Here are some photos from Bicentennial Park with different forms of inspiration. And some photos of the existing Discovery Centre, which includes a small-scale building, elevated function hall, and two pavilion areas, nearby bridges and walkways. The project will address three chosen UN sustainability goals that will work together to design a concept. 12, responsible consumption and production. 14, life below water. And 15, life on land. There's a unique opportunity to build with local and innovative materials, using water ecosystems to drive design, and to further enhance Sydney Olympic Park's great initiative to protect local biodiversity in future development. Research and development will undergo two phases: studying natural growth patterns as a structural language, and studying biocomposite materials, biopolymer and mycelium, that could work with the structure. The chosen structural and material language will drive the design of a discovery centre in Bicentennial Park. Phase 1. Biological growth is not uniform, it's differential, responding to environmental stimuli and thus producing the formation of macroscopic shapes like these. You can simulate this pattern in Grasshopper by segmenting a curve and letting it expand without any of the segments touching or overlapping, by adjusting the parameters of the number of segments, radii, and strength. For prototype 1, I tested the expansion of a curve within a boundary, producing 10 iterations of 10 stages of growth. I stacked and lofted these and printed the result in PLA filament. For prototype 2, I tested the growth pattern on a surface with different densities of growth. I simulated it on a range of surfaces, studying which surface would be ideal for this pattern structure. I did some test 3D prints to see how the printer behaves with this pattern, testing flexibility and also the limitations of this method. Moving on to materials, I looked into biocomposites, as standard building materials have a significant impact on our environments and resources. Some plastics have high recyclability rate and strength to cost ratio, which was promising, which we'll look into later. But I first studied mycelium as a building composite, the root system of mushrooms that is combined with agricultural waste to produce a strong, versatile composite using a template. I tested the material by growing it myself to see how it behaved, but it ended up just being an interesting side project. Next, I looked into biopolymers, more specifically cellulose-based like algae, as I could easily harvest from site. They would be refined and 3D printed into modules that would form larger structures. From its state as a raw material through extraction and manufacturing to eventual decomposition, the material is grown from its environment, and if 3D printed on site, the architecture will also be grown from its environment. Regular PLA filament can be readily replaced with biopolymers. They have similar material properties, but are biodegradable, so would require a waterproof layer or could be designed to decompose naturally. Research led to an intention to design multiple iterations of differential growth on a surface as a solid using algae biopolymer. I'll design a small yet expandable factory to support the production of pavilions across the site. The public will be able to view the process and there will be less harmful algal blooms across the site. Some early concept sketches included a structure kind of along the side of water and path, but in the end I decided to reuse the existing Discovery Centre to enhance the main building and connect it with the pavilion areas around it. Algae will be sourced on site, so transport considerations have been made. The project will test the use of differential growth as a stack and lofted sculptural wall and column system and the pattern simulated on a surface, becoming rib-like pavilions off the block of program. The main building will house manufacturing, production, research and education areas. The circulation corridor will include a public walkway with the columns and visual access inside, as well as linking to previous function hall, and will also now be a cafe and education theatre above. This is the site, located at a node intersection of multiple paths, a good spot to draw people in. A small road will be made to connect to the existing car park to help with vehicular and pedestrian circulation. This is the ground floor plan with the public walkthrough and seating area. Landscaping takes inspiration from the differential growth pattern, another experience of this pattern. The first floor will be with a viewing gallery of the sculptural walls and a green roof space with the other programs. The southern elevation gives an idea of the scale of the sculptural walls, aimed to be monumental spine to the new Discovery Centre. This section shows the internal space in that corridor, as well as pavilion structures on the other side. This is a render of the southern facade with seating areas and bike parking, a render of the entrance to the public walkthrough and visual access to the interior. Over the next century, the Discovery Centre building will expand and continue outputting pavilion structures across the site. As it expands, so will the education, classroom and cafe areas too. While this is conceptual at this stage, I'd like to design parasitic structures that will revamp existing and perhaps deteriorating infrastructure across the site to continue keeping the site healthy and functional.